Okay, guys, this lesson's going to be on digital electronics. It's going to be a short lesson, and the reason for that is because you already know the material. You already know the mathematics behind. I'm going to take this hat off. You already know the mathematics. In fact, I'm going to take this coat off too. I'll leave it on. You already know the mathematics behind digital electronics. It's Boolean algebra, truth tables, simplifying, and that kind of stuff. What's different is that you now have symbols, graphical symbols, that represent logic gates that you can build circuits out of. Remember, because I told you a long time ago that Boolean algebra is the language of the integrated circuit, and now we're going to represent that in circuit form. So behind me here, actually in front of me here, I have, oops, straighten that color. I have a sheet that you should have at least an electronic version of, and it has the digital electronics logic gate symbols. Okay, and I'm just going to go over those with you, and the purpose of this video is just to give you some goofy ways. You know what, I'm going to take this mask off. Sorry if I ruined everything for you by taking the mask off, but I think I've been compliant enough. But I'm going to show you some goofy ways to to remember which circuits are which. Okay, and here we go. This triangular circuit here that does not have a bubble on the end is rarely, if ever, used in ACSL, American Computer Science League, digital electronics. If you have a 0 going in, false, it'll just be false. Nothing changes. It's just called the buffer, and if it's ever there, on the rare occasion that they sneak it in on you on the worksheets or the quizzes, well, there's no change. So if it goes in true, it comes out true. If it goes in false, it comes out false. This one here, which is the second one on your sheet, your note sheet, has the little negation bubble. Okay, and so it's just the not. This is not. It's the not gate, and it's the triangular one. And if you have, it only takes one input as opposed to the others, which take two. And if something comes in true, then it negates it and turns it to false. And if something comes in false, it changes it to true. Okay. The next one is it's kind of you look at it and you think it's kind of a D shape, and it's and. It's the AND gate. And with the AND gate, you want to say, oh, well, AND has a D in it, so it looks like that must be an AND gate. But if you look at them all, the XOR gates and the OR gates, they all look like Ds. So we need something a little bit better to help distinguish between the ANDs, the ORs, and the exclusive ORs. And here's the way I look at it. This is a bit cheesy, I know, but it's going to get worse, I promise. So this pen works. But here's how I look at it. It's the back of the gate, or the front of the gate, where the inputs come in. It has a flat entry, and the A in AND, if you think about it, is made out of 3 straight lines. Okay, so this entry into the AND gate is flat, like the 3 lines that make a capital A. Those are all flat. Okay, and that's how I like to distinguish the AND gate and the NAND gate, which I'll talk about in a second, from the OR gates and the exclusive OR gates. Okay. Now the next one on here is the negated version of it, where it comes in as an AND, but whatever, you know how AND, the only way to get true with an AND is if the inputs are both true. Okay, anything else would make an AND false. Okay, So 0, 0, 0, 1, 1, 0, those would all make an AND gate false. But the NAND gate is just the opposite of AND. Okay, everything that makes it true, makes AND true, is going to make NAND, or NAND is short for not AND. Anything that makes AND true is going to make not AND false. And so what would make the NAND or the not AND gate false? The only input that would make it false would be the same input that makes AND true, which is both entries are true. Both inputs are true. And so to make a NAND, that's what this is, not AND. You basically think of it as two operations built into one. First, you do what you would with AND, and then you flip all the switches and make them negated. So with AND, you had X and Y, and this is X, and this is Y. You got possibilities of 0, 0, 0, 1, 1, 0, and 1, 1. Then with AND, X and Y, whether that's that kind of an AND or that kind of an AND, X and Y. This is going to be false, false, false. This is the only one that's true. But with NAND, X, not AND, it's just the opposite. These will all be true, and this one will be false. Okay? So hopefully that's okay. How do we remember that? A's are made out of straight lines, and this has a straight entry point. Okay, let's look now at, I hope I can erase this. Not upset anybody, because it's a video. You can always rewind, right? Okay, for the OR gate and the NOR gate, the not OR gate, you have not a flat entry like you do with the AND, but you have a curved entry. And it still sort of looks like a D, like a capital D, but the entry is curved, and this is OR. And okay, to remember that, you know, kind of running along the same lines as with the AND. If you look at the beginning of it here, the place where you enter, it's curvy like an O, okay? So an O, like an O in OR, okay, has the curvy nature to it as well. And so that's how I distinguish them. So for the NOR, that's going to look like the OR with the negation bubble. So with X or Y, let's do that again. Okay, with X or Y, let's hope you can still see that. A lot of glare. With X or Y, the only way to get false with an OR is if both inputs are false. So this is the only false when we do OR. True, true, true. So X nor Y is going to be the opposite of that. The only way to get true with a Xnor, or excuse me, with NOR, is if both the inputs are false. That would give you true. False, false. That would give you true for that, and all the rest of these would be false. They're just flipping the switches of the OR. Okay? A lot of glare there. Sorry about that. I'll put my shadow on it for a second, and maybe you can see it. All right. The next set of symbols is a lot like the or. Looks a lot like the or. They all look the same anyway. But with, I'm going to go ahead and erase these. Okay, the XOR, exclusive OR, looks just like the OR, except that it has an extra tail behind it. Okay, so it looks like the OR. It has that curvy opening, just like the OR does. Okay, not flat like the and but it has an extra tail, and that's how we're going to remember XOR. It has the extra curve at the beginning. Like I said, I know that's cheesy, but it works. Okay, and so the negated version of that is going to be Xnor. Okay, but it has another name, which I'm going to tell you in a second here. It has another name, and that is, well, let's remind ourselves what XOR does. Okay, if we have X and Y, 0, 0, 0, 1, 1, 0, and 1, 1 are our only possible inputs with an ordered pair. Okay, then X XOR Y, or A XOR B, whatever, is going to be true whenever the inputs are opposite. Whenever the inputs are the same, it's false. Okay, we know that. We already know that. So this one's false, true, true, false. Okay, for exclusive OR, the only way to get true with XOR is if the inputs are opposite of each other. You have one that's false and one that's true. And that would make XOR true. So 0, 0, and 1, 1 would make XOR false. Now, Xnor, the negated version, oops, I didn't put that up there. Now it's the negated, if you can see it. Okay, now it's the negated version of XOR. Okay, it has the negation bubble on it. That one is going to be the flipped switches of the XOR. So whatever made XOR true is going to make Xnor false, and vice versa. So for Xnor, since these are false, true, true, false, when the inputs are the same, the outcome is now going to be true. Okay, so the 1, 1 will make Xnor true. 0, 0 will make Xnor true because it's the opposite of XOR. And because of that, because of the fact that Xnor is true whenever the inputs are the same, it's also called Equiv, or equivalent, because the inputs are equivalent to each other when it makes them true. And so Xnor is also called Equiv for that reason. Okay, and I think that should about do it. Anybody think of anything I need to add? So, great.